Hi, everyone. Welcome to the video lecture for weeks 8 and 9. So I thought it would be useful to go over a little bit on Bayes' theorem and to give you an introduction to Dutch books, which is a way of justifying why we want our beliefs to cohere with probabilities. Okay, so let's get started. So Bayes' rule, remember, gives us a systematic way of determining the relationship between the probability of A given B and probability of B given A. I remember that we derived in class that the probability of A given B, this is the baby Bayes, is equal to the probability of A times the probability of B given A over the probability of B. Right, so now you can figure out what the probability of A given B is just by knowing the ingredients of probability of A, probability of B, and the probability of B given A. And we derived a more complicated version of Bayes' rule, which you can derive this, this equation over here with the rule of total probability. And we did that in class, and you can look over the slides from that. You might ask, well, okay, I see this mathematical formula, but why should we care about it? But remember that the whole point of the class is that we want our inductive logic to help us in assigning inductive probabilities to arguments. And what Bayes' rule allows us to do is to have a way of formally determining how we should update our belief given a piece of evidence. So I might have a particular belief about a statement, and you show me a piece of evidence. And what Bayes' rule allows me to do is to have a systematic way of updating my beliefs based on that evidence. And not only is it a way of updating the beliefs given the evidence, but it is, many people think, the right way, or at least a very good way. So what do we mean here by updating our beliefs given a piece of evidence? It means that if you have a probability or a belief on a particular hypothesis, call it H, then if I give you a piece of evidence, you know how to get a new belief on this hypothesis. So the new belief you'll get, which is here the probability with the subscript new of statement H, is equal to your old probability of H given E. And so let's see this visually. It usually helps me, and we'll go through an example in a second. So you'll start, right? I start off at a particular time with a probability of a particular statement. Say my hypothesis is that it will rain tomorrow in Los Angeles. And I believe that with a 20% chance. And now you show me a particular piece of evidence. For example, you show me that there are some dark clouds in the sky. And what Bayes' rule allows me to do is that if I have a well-defined probability of H given E and a probability of E, then I can get a new probability for this statement, which is, well, that it will rain outside. So let's look at an example. This is very abstract, and I hope I can make it more concrete with this example. So this is very similar to the practice question that I put for week 8. Now, I will note that there is a little glitch in that practice question, and it was actually done on purpose. So you'll see that the numbers here are a little different. If you can find what this glitch is, and the first person to email me, I'll give them a little bit of extra credit. So let's go through this example. Suppose that Jerry's beliefs are well modeled by probabilities. Given the background information he's been exposed to, he believes that the Earth will heat by at least 1.5 degrees Celsius by 2050 with probability 2/5. So we can call this statement, let's call it G for global warming. G is the statement that the Earth will heat with probability 2/5. Or sorry, the Earth will heat by at least 1.5 degrees. And what I've told you is that Jerry has a probability of G, which is equal to 2/5. So note that Jerry doesn't have a high credence of global warming being true. But now, he also does not believe it's very likely that it will snow in Irvine in March. Right? So let's say that S is the statement of snow in Irvine in March. And the probability that Jerry assigns to that is 2/10. He only thinks this with probability 2/10. So the probability of S is equal to 2/10. But Jerry has this belief that he does think that if the global warming is true, or that if the Earth will heat up by 1.5 degrees, then it would mean that the climate is messed up in a particular way that would make it more likely for it to snow in Irvine in March. So how do we write this? In particular, he believes this with probability 3/10. Well, what this means is that for Jerry, given that the theory or that global warming is true, remember, he doesn't believe that with very strong probability. He only believes it with 2/5, right? But given that it's true, if you tell him it's true, then he thinks that the probability that it will snow in Irvine in March will be higher than just his unconditional probability that will snow in Irvine in March. Namely, he'll believe it with 3/10. So note that probability of S given G is higher than the probability of S. And now we might ask, well, given that Jerry actually observes that it snows in Irvine in March, right? He's not observing that the theory is true. He's observing that it snows in Irvine. What is his probability that the Earth will heat up by at least 1.5 degrees by 2050? And so in particular, what's the probability that his new probability, right, of G, and here this will be the new probability of G, which is that that global warming is true. Well, it's the old, and all these are old probabilities, will be the old probability of G given the piece of evidence, right? Which is that it snows in Irvine in March. Okay, and so what is this by Bayes' theorem? Well, it's a probability of G, we know, times the probability of S given G over the probability of S. And so now we just plug in, we have all of these. We don't have to do any fancy footwork here. So it's just 2/5 times 3/10 over 2/10. Now, if you work this out and you just do the algebra and have it written down over here, this is equal to 0.6, right? Or 6/10. Now note that Jerry went from believing this G from 4/10 to believing it with 6/10. So he increased his belief that global warming is true, given the evidence that it snows in Irvine. So this is what Bayes' theorem and Bayes' rule allows us to do, is that it allows us a way of saying, well, if you are rational, and we'll get to why in the second part of this video, but if you're going to update in the best way, then you should update using the rules of probability. And here's what it says is, well, Jerry who had these, right? You might think, well, he shouldn't have had this belief in the first place, right? It shouldn't have been only 4 out of 10. It should have been higher than that. But given that he believes it with only 4 out of 10, and given his beliefs on the evidence and how much it confirms, then the rational way of updating will be using Bayes' rule. And we see that it makes intuitive sense, right? Jerry observes that it snows in Irvine. He thinks this is very unlikely. And he thinks that if global warming is true, then it will snow in Irvine. Then it's more likely that it snows in Irvine than if just this unconditional probability that it snows in Irvine. So we see that Jerry went from 4 over 10 to 6 over 10, right? And that's intuitive. He got evidence, and so he updated. So now he believes that global warming is true with a higher probability. Okay, so let's get back to the slides and see, why should we think that Bayes' rule, but in particular, just probability theory, is a good way of updating our beliefs? So here it will help to look at the expected value of a gamble, or how much money we make from a particular gamble. So remember that one way to measure the attractiveness of a gamble is to look at its expected value. And basically what the expected value does is it measures the average winnings you'll make from the bet. So we went over this in class, right? But suppose I propose to you this particular game. I toss a fair coin. If it's heads, then I give you $10. And if it's tails, then you give me $1. Right? And so now I want to calculate the expected value of this game for me. So I list all the possible outcomes, which are heads and tails. I note their probabilities, right? I told you it's a fair coin, so it's 1/2, 1/2. The amount won. So for me, maybe you can think about this for a second. For me, if it's heads, then I give you $10. Then I lose $10, right? But if it's tails, you give me $1, so I make $1. And then one of the crucial steps is you multiply the probability times the amount won. So you multiply 1/2 times my -10, which is -5, and you multiply 1/2 times 1, which is just 1/2, or 0.5. And then you add these all together to get the sum, which is just the expected value of gamble. So for this one, it's -4.5. So it's negative. So note that, again, this is just review, but a fair bet is one where you can expect to win $0, right? If we play the coin game and I give you $1 if it's heads and you give me $1 if it's tails, then in the long run, none of us will make money. But if the bet has an expected value greater than 0, then it's favorable for you. And if it's less than 0, then it's unfavorable. And this makes sense, right? This game, the expected value for me is negative, and you can see that it's unfavorable for me. But unfavorable bets are not the same as Dutch books. And we're going to see. Dutch books are stronger. So let's get to these Dutch book arguments. What do they say? So they come back to this philosopher called Frank Ramsey, who has done a lot of great things. I encourage you to look him up. But the Dutch book argument is really an argument. So let's look at the premises of the argument. Premise 1 is that beliefs that license senseless behavior are irrational. Okay, so one of the premises of this argument is saying, well, look, if you have beliefs that we all agree leads you to do senseless behavior, then we'll call you irrational, or we'll say that your beliefs are irrational. This doesn't seem very controversial, but the crucial step of the argument is, well, if your beliefs violate the rules of probability, then they'll lead you to do this senseless behavior, right? And you might ask why, and we'll see why. But if you accept both of these premises, then it follows that beliefs that violate the rules of probability are irrational. And let's see an example, right? Where Dutch books are very complicated. There's a whole theory behind them. But let's see an example of why or how violating the rules of probability can lead you to senseless behavior. But to do that, we're going to have to operationalize the notion of belief. So remember, we're going to do that by equating beliefs with betting behavior. Right? This is one, but not the only strategy for operationalizing beliefs. There might be others, but what we're going to do is say, well, your beliefs, we're going to operationalize that with betting behavior. And just a quick note again on, you might think, well, this is a little bit weird, but in science, especially social sciences or like psychology, we practically never actually measure the thing we're talking about, right? If I want to measure intelligence, I give you certain tests, and I might tell you that this somehow tracks this vague notion of intelligence. But really what we're measuring is how good you're doing at a particular test we've contrived. And it's going to be something similar that we're doing here. But what we'll do is we'll say that a person believes a statement with a probability X. What that means is that they're willing to pay X amount for a gamble that returns $1 and $0 on not X. So let me restate that. What that means is that if I believe something, if I believe a statement with a probability 0.25, what that means is I'm willing to pay 25 cents for a gamble that returns me $1 if the statement happens, and $0 if the statement doesn't happen. So here there is a typo, so I will so it's not on X, right? It's on the statement. So I will believe a statement, let's say a statement A, $1 on A, and $0 on not A. So let's, so apologies for that. So let's go over this definition again. So what we'll do is we'll say that a person believes a statement A with probability X means that they're willing to pay X amount for a gamble that returns $1 if A happens and $0 if not A. So let's do this with the example again. Let's say I believe that it will rain tomorrow with 25% chance or 0.25 probability. What that means is I'm willing to buy a bet for 25 cents that gives me $1 back if it rains tomorrow and gives me no money back if it doesn't rain tomorrow. And it makes sense. If it rains tomorrow, then I make the $1 back minus the 25 cents I paid, so I make a profit of 75 cents. And if it doesn't rain, I lose 25 cents. So I make more than I lose, but that makes sense because I don't really believe that it's going to rain tomorrow. Right? I only believe it with 0.25. Okay, so what we're going to do now is we're going to go through an example with this definition of, or with this operationalization of belief. And we're going to see how violating the rules of probability leads to senseless behavior. Namely, it leads you to a Dutch book. So let's go again back to the over here. So let's look at this example. So suppose there's a coin, and I think it's biased, but my beliefs, which again are operationalized by my betting behavior, do not satisfy the rule of probability. In fact, I think that the probability of heads is 0.6 and the probability of tails is 0.6. And so the question asks, well, construct a series of bets such that I'm at a loss no matter whether the coin lands heads or tails. So I strongly urge you to pause the video now and to try to do this exercise with the definition I've given you. Okay, if you've paused and you've gotten stuck and now you're looking at it, then we can start. So step one is to say, well, here are my beliefs. Do they really violate the rules of probability? And yes, they do. So remember by rule one that the probability of a tautology is equal to 1. But now we know that the probability of heads or tails is equal to 1, right? Because heads or tails is a tautology. If I flip a coin, then it either lands heads or it lands tails. And that is the whole space, right? If we imagine it with our sample space, then 50% of the time it's going to land heads, and 50% of the time it's going to land tails. And that's the whole space. Okay, so we know that this is equal to 1. But here, by rule 4, we know that this is equal to the probability of H plus the probability of T, right? The probability of heads plus the probability of T. And remember that rule 4 only applies if H and T are mutually exclusive. But here they are, right? It can't be true that the coin lands heads and tails at the same time. And right now, you might already begin to see where the issue is coming, or how we're violating our rules of probability. Well, because probability of H is 0.6, right? I told you that over here. And the probability of tails, that I believe it with 0.6, and that's equal to 1.2. But 1.2 is not equal, right? These two are not equal to each other. And so we're violating our rules of probability. And so you might say, well, that's fine, right? It might look weird on the math, but why should I care if I violate the rules of probability? And what we're going to show is, well, if you operationalize your beliefs with betting behavior, then you should care, because we're going to construct 2 bets and you'll be willing to accept both bets, but you're going to lose no matter what happens. Okay, so let's see. Let's construct these bets. So bet 1 will be, well, we're Dutch booking me here. So it'll be, I buy a bet on H for 60 cents, right? I believe heads will happen with 60% probability. And so I'm willing to buy a bet for H on 60 cents. So what that means is, if coin lands on heads, I make 40 cents, right? Because I get $1 back. So go back to the definition of operationalizing beliefs. I pay the bet for 60 cents and I make $1 back. So I have $1 minus the 60 cents that I paid for. So that's a profit of 40 cents. But if the coin lands on tails, what happens? Well, I lose the 60 cents that I bought the bet for. Okay, now let's look at another bet on tails this time. So I'm willing to take bet 1. Note that I'm willing, if I have the beliefs that the probability of heads is equal to 0.6, then I'm willing to take this bet, because that's just how we've operationalized beliefs. And similarly with tails, I am willing to buy a bet on T for 60 cents. So what happens, right? If the coin lands on heads, then this time I lose 60 cents, right? Because I bet on tails happening, but heads comes up. So I bought the bet for 60 cents and I just lose the 60 cents. But if it tails happens, then I make 40 cents. And again, I buy the bet for 60 cents, but I'm betting that tails happens. Tails actually happens, and so I get $1 back. But I paid for it for 60 cents, so my profit is 40 cents. And now if I take both of these bets together, the weird thing that happens is that if we flip the coin, I'm going to lose money in both cases, whether the coin lands heads or the coin lands tails. So let's, okay, so I'm zooming out a little bit here. So let's look at the outcomes. Right, we have heads and tails, right? The actual outcomes. Let's say we flip the coin. What happens on bet 1 for these? What are my profits? Well, let's look. On bet 1, if the coin lands heads, I make 40 cents, right? I'm buying the bet for 40 cents, so I'm at plus 40 cents. And if it lands on tails, then I'm at minus 60 cents. Now note that there's nothing irrational so far, right? I just believe for bet 1. There are some cases where I win 40 cents and some cases where I lose 60 cents. That's perfectly fine. What's weird is that you're willing to accept another bet on top of this one that will make you lose all the time. So let's look at bet 2, what happens there. Well, on bet 2, if it lands on heads, then remember, I lose 60 cents. So I'm at minus 60 cents. But if it lands on tails, then I make 40 cents. Okay. Now, note that if I only focus on bet 2, then this is also fine, right? There's some cases where I lose 60 cents and some cases where I win 40 cents. But the weird thing is if we take them together. So the total winnings, if it lands heads, well, it's plus 40 cents minus 20 cents. So it's minus 20 cents. And if it's tails, I lose 60 cents and I win 40 cents from bet 2. And so it's minus 20 cents. And so no matter what happens, I'm losing money. And this is the senseless behavior that we're talking about. It's senseless for me to go into a bet thinking, or to accept bets, thinking that I could win money, but in whatever happens, I will lose money. Right? And this is stronger than having a negative expected value, because in the expected value, sometimes you can have a negative expected value, but still expect that if, for example, heads happens, you win. So just go back to the example from the slides and you'll see that. But here it's saying, well, no matter what happens, you're going to lose money. And so this is a senseless behavior. And actually, you can construct a bet like this for any violation of the rules of probability. So here we've only violated, well, rule 4 and rule 1, but for any violation, including the definition of conditional probability, and so which is essential for deriving Bayes' theorem. And so if you violate those conditions, you are always going to be subject to a Dutch book. And the Dutch book is these bets which no matter what happens, you're guaranteed to lose. And so this is a pretty strong case, right, for probabilities, for wanting our beliefs to cohere with probabilities. At least if you think that this operationalization of beliefs with betting behavior is plausible, then you should want to have your degrees of belief cohere with probability. Okay, that was it for today. I will see you all on Wednesday, and I'm looking forward to our last class.